Welcome to the lecture on Descriptive Data Visualization, part of the Principles of Data Visualization lecture series. Now, when we discuss data visualization, we might have a curiosity of how did it come to be? So in the beginning, there was the graphics movement, and the graphics movement helped lay the groundwork for information visualization. Work on information visualization helped lay the groundwork for our modern data visualization practice. So a quick question. In the beginning, when did graphical visualization begin? What do you think? Was it the 1930s, 1960s, 1990s, 2000, last year? How about the 19th century? So what you see in front of you are a number of early examples of graphical visualization created by a Scottish engineer named William Playfair in the 19th century. So on the top left-hand side, you will recognize similarities with the modern trend chart, as well similarities with the area chart. In the center, you'll see the predecessor of our modern bar chart. And then in the bottom right-hand corner, you'll see an early predecessor created by Playfair of the pie chart that you might recognize as the pie chart. So graphical visualization has been around for quite a while. In certain ways, there's nothing new under the sun. In other ways, there's a number of new things that have emerged in the field of data visualization. So we will walk you through, and the natural place for us to start is with the graphics movement. So the graphics movement was ushered in by Jacques Bertin, Frenchman. He introduced the concept of graphical encoding. And this was in the late 1960s. Bertin basically established that graphics was not necessarily artwork. It's a system of signs that convey meaning. And this was a very important distinction, that whatever those representations were, and there was nothing to be taken away from the creativity of the design, but the importance of those designs, were that they conveyed meaning. So in essence, Bertin gave those creative objects utility, and he emphasized the utility of those visual objects. He also brought forward the concept that we will learn to see relationships in data, that one of the important roles of graphical visualization is seeing those relationships. It's one of the important features that's available in graphical visualization. And that in general, graphic visualization is a process of finding the right questions to answer. And that's fairly interesting in that it parallels a lot of the same thinking from the statistics movement that we'll refer to in an upcoming lecture. So let's take a look at this example from Bertin, provided by Bertin. This is a data table. We see across the top, these are months. So we have January, February, March, April, May, June, July, August, September, October, November, and December. So basically all the months represented in the column headings at the top of this data table. Then over on the right-hand side, the tags for the rows we'll see are different customer groups. And we'll see that those are numbered there, 1 through 20, and they have different descriptive terms. So we have female clientele, local clientele, so basically local folks, folks from the USA, and I should relay. So the overall understanding of this data that we're looking at, this is a data set from a hotel. basically an equivalent data set from the hospitality industry. And what we're seeing here is customer groups with a cross-section of months, and then the numeric measure that's represented in each of these cells is the frequency or the count, or how many individuals booked a room and with that particular cross-section in that month and from that particular customer group. And proceeding on through, we have customer groups from South America, from Europe, Middle East and Africa, Asia. We have businessmen, tourists, direct reservations, so those would be folks that called the hotel directly, those folks that booked from a travel agency, air crews, which basically refers to those who are pilots or flight attendants, or those folks that are traveling with an aircraft that book the hotel. Young clients, folks that are under 20, essentially sort of the minors group. And then it splits into some age groups of demographics, so 20 to 30, 35 to 55, and then folks over 55. The price of rooms, so folks that basically are budget shoppers. Length of stay, so we have a measure there that determines how long folks stayed. And then we have some data that is percentage of occupancy in different months. So this would be a percentage out of the number of nights that someone could have stayed in a particular hotel. What percentage of those nights was someone staying in the hotel? And then we also have particular conventions that are highlighted in each of those months. So we see that we had some conventions in April, May, June, as well as some months later in the year. So our measurement changes a little bit, and we can tell that. So when we get to basically row 16, our measure changes there. So on 17, it's a measure of price. 18, it's a measure of number of weeks. And then occupancy, as we just described, it's a percentage. And then conventions is sort of a binary, whether there was a convention or not in that month. Okay, so this is sort of the setup and framework of a data set presented by Bertin. Now, Bertin then proceeds to communicate with us that there are 3 different types of questions related to a data set that we should ask. So we'll start with the first question type, the elementary question. So with the elementary question, we're basically talking about a cross-section of the X and Y. So if we, on the X and Y axis, we find a column heading as well as a row heading for the group. We go to the cell for that cross-section, and we can ask ourselves a question from those 2 headings. You know, as an example, what in the month of February or March, what did folks over 55? What was their frequency of staying? How many people booked a room? So that would be an example of an elementary question. Then we have an intermediate question. So the intermediate question is questions we might ask perhaps after a processing routine that we'll talk about in a minute, that corresponds to more than one particular row or column. And you see highlighted that on both the X and the Y axis, an intermediate question would be a question that we would ask for a group of months, so perhaps for a season, and a question that we might ask for a number of individual groups as a set. So another example might be we might ask a question for all age groups. And then the third type of question is the overall question, encompassing a much larger view. The overall question would be question types that are asking what's going on with the entire data set. And you see sort of the much larger circle encompassing a much larger number of cells there. So taking a closer look at the elementary question, so we have an example here where a question we might ask is, how many females stay at the hotel in February? Or the question asked a different way, how many females book a room in the hotel in February? Okay, so we will take the cross-section. So we'll take basically the x-axis, we have a column header of February. And then on the y-axis, we have our clientele, female. And if we look at the cross-section of that, the measure that answers our question is 21. Basically, there were 21 bookings from females in February. So that should give you a real good solid example of an elementary question. At this point, Bertin takes us to a processing routine. And a processing routine we might think of as a modern algorithm, some type of treatment or manipulation that we would provide to our data measurements to help us understand our larger questions, so our intermediate or overall questions. And so what Bertin does here is he gives us a fairly simple processing routine, fairly simple but also very effective processing routine, where the mean of each of these rows, for example, female clientele bookings or local clientele bookings. So we take all of the measures for that particular row and we find the mean. And then the processing routine is a simple encoding of, for each cell, in place of its measure, we will instead either completely shade or black out that cell if the measure was greater than the mean. If the measure was less than the mean, we give the other option in a binary system, basically to leave it blank or open or null. So what that does, what our processing routine does, is given the mean for each row, it goes through each cell and assigns either a completely shaded in or a completely null or open visual representation or visual encoding, so that we can quickly visually tell for each cell if it was above or below the mean. Okay. Now from there, once we've applied that processing routine, we can then do some things like we could sort, or first we could just look at what do we see? Do we see any patterns in this particular data set? Because now we have sort of this binary encoding with each of the cells, and visually we can use our human capability of processing visual information to determine, wow, are there a lot of particular rows that go together? Should they be sorted together because they have a consistent pattern across the months? Or is there a number of things that might be going on across several months that have a consistent pattern? And so what we see highlighted here in our intermediate question, we'll see relationships of particular months. So if we look closely here, we'll see in December, January, and February, that's a seasonal pattern. So we see the winter pattern, or the pattern of bookings that goes on in the winter. So we can see there's a very clear pattern in December, January, and February where there are a greater than average number of bookings. And we can say that it's a greater than average number of bookings because we see all the shaded in cells that from our processing routine, by definition, are higher than the mean. As well, we can see that pattern repeats. So there seems to be a seasonality. Every 3 months, it's sort of below and above, alternating below and above pattern where there are more bookings or less bookings depending on the months. And as I mentioned, we can group characteristics either on the X or the Y axis. And if we look at some of our different groups that seem to have this consistent pattern, we see air crews, young clients, basically minors, as well as older clients that may be over 55 years old. We have some youthful adults in the 25 to 35 year age group, as well as female and local clientele. So each one of those group classifications seems to have the same pattern that we could create that group called recovery factor for the winner. Then we move on to insights from the overall information level. And here we're looking at a much broader view. What's going on with the entire data set and what insights can we get out of that? This chart that that's in front of us, it is in fact the same chart, but it's been reorganized, so basically based on our patterns. And we can take away from this certain insights. So we'll see across the top. In December, January, February, and March, we have a consistent pattern of local clientele as well as female clientele. We also have a pattern in July and August where we have tourists, direct reservations at the hotel, and folks that are 35 to 55 years of age. So we see that consistent pattern here. And then we also can highlight here, we have active and slow periods. That's our seasonal. So over on the right-hand side there, that seems to be prevalent where our groups are percentage occupancy and length of stay, as well as discovery factors. So the groups there are conventions, business people, agency reservations, South America, recovery factors that we've already discussed before, as well as winter-summer pattern, and then summer only. So this gives us several unique insights that we can point to of what types of groups are staying in the hotel at different times in the year and what their peer group might be. So that takes us through the 3 different questions that are different levels of information that Bertin suggests that we should be asking questions. And it also brings us to a visual analysis process. So Bertin describes the visual analysis process as a series of 5 steps. First, we define the problem or objective. So in our example, we want to know who's staying in our hotel. Basically, who's booking those reservations, what's their peer group, what might be some of the influencing factors in booking those reservations. Second step, we structure the data. Okay, so good example of structuring the data. We set up our data table and an XY axis data table, and this is the way that we've structured the data. So we've applied some kind of structure to it. Third step, we're adopting a processing technique. And so if you remember our processing technique, we applied basically a shading. If it was above the mean, We encoded it with a darker shading below the mean, a lighter shading. And you'll also find that there is some shading that goes on. So some of the cells that may have originally had a darker shading, or I suppose perhaps a lighter shading, but didn't necessarily fit the pattern, may have been shaded with an in-between shade, which gives us more information, not less, to understand that those existed, but in order to see a particular pattern, we may set the shading somewhere in between the two binary options. From there, we simplify without destruction. And basically what this means is we might sort. We want to find different patterns, or we might filter, or we might reorganize the data into a more meaningful way where we can see the patterns a little bit better. And then once we've simplified without destroying data, we can then go to communication. So we would create sort of visual representations that would communicate what we'd found. And probably some of the best examples of that might be the different groupings that we had in the overall question, or the third different level of information. Now, Bertin is also credited with developing the 8 basic variables of visual encoding. And these different variables basically are the underpinning of all visual representation that we see in our modern data visualization software. In one way or another, all of these track representations with the software that we might utilize trace back to how do we represent information graphically, and then one step further to Bertin's initial principles on here's how you can represent data in a visual way. So these 8 variables have really stood the test of time. To date, there hasn't been a new set that has been brought forward. There isn't a 9th variable. The 8th haven't been successfully overturned. So these are basic essentials. Understanding these are basic essentials to understand data visualization in general. So we will go through each of them, and yeah, I think with a little luck, everyone will come away with a more fundamental understanding of what they've been seeing all this time. So let's start off with the first 2 variables at the top. So the X and Y dimensions. So probably all of us are used to plotting points on an X and Y axes. And that's what is represented here. So if you can imagine a plane, and a plane might be similar to a plate of glass that we're holding. You can rotate that plate of glass in any direction from a 3D standpoint, but it's a plate of glass. And on that plane, we might have points, basically plotted points. And so in the first 3 cells that you see represented there on the X and Y, where it says 2 dimensions of the plane, this first row, first couple of variables that we're working on, you'll see different plotted points in different XY positions on that plane, or on that plate of glass. So the first one is pretty much in the center on the X, but a little bit below the center on the Y. Then the second one is a little bit above the center on the Y, and still remains in the center on the X. And then the third, sort of a little bit below the center on the Y, and in the center on the X. So we can basically just see 3 different plotted points with XY coordinates on a plane. So that is the first way to understand the X and Y variables. Now, there's also a way to represent lines and areas. And we will circle back around. Once we've gone through all 8 of the variables, we will circle back around and discuss both lines and areas. So we'll move on to the next variable, the third variable, which is size. And this is known as one of the z variables. So if you think about a z-axis, so this would be one of the 2 variables that we can use on that z-axis. And you'll see different representations of size. So as a plotted point, in the first cell by size, you'll say, oh, that's a very large plotted point. The second one, that's sort of a medium size plotted point. And then the third one, that's a much smaller plotted point. So what pretend is representing here with this variable is the size of the mark that we make. So we might make sort of a dash like this. It might be a very large circle in the center. It might be a medium-sized circle, and then the third cell there is a much smaller circle. But we're using size as a variable representation. And in order to contrast between the point on the XY and size, remember that the technical definition of a point might be the sharpest end of a compass or a needle that we make in a particular location. It has no particular size. It's just that particular point, that particular location. It's only when we add in another variable of size that we get a smaller or larger circle at that plotted point XY location. Now we move on to our fourth variable, value. So value is also a z variable, and we will see the value represented this way. In the first cell, that's the binary value of it's on or encoded, filled in, shaded. Second cell, same way, it's on and encoded. And then the third, we'll see it's off, basically the null set, not shaded, or the least shade possible. So the difference between those is a value. It's on or it's off. It is shaded or it's not. Then we move on to the next 4, or the last 4, which are determined to be differential variables. And let's talk about those. So the next one's texture. So imagine texture in this way. In the first cell, those are what's represented there are very large ridges. And so if I moved my finger across them, they would be very bumpy. Then if I moved to the second cell, those would be some smaller ridges. So it wouldn't be quite as bumpy, but I would clearly feel an up and down with my tactile touch there. And then the third cell there, it would be fairly smooth. If I ran my finger across that, I might not notice any bumps at all. That is texture. Then we move on to color. So the 6th variable is color, and you'll see represented there in the first cell, blue, then the second cell, red, and then the third cell is green. Now, many of us, when we probably first came to the class, first came to this material, we probably had a notion that color was one of the strongest variables. But we see as it's represented on the chart here that that is not necessarily the case, and I'll explain why in a minute. Then we move on to orientation. So with orientation, I can create unique visual impact basically by changing the angle of the representation. So we see here with orientation, the first cell, we see it's straight up and down. Okay, so that's basically running from the 0 to 180 on the compass. If we move on to the second cell, so we see that might be at a 45-degree angle. Then we move on to the third cell. So that might be something greater than 90, maybe it's a 110 or 120, something like that angle. And so we can see uniqueness between these three different marks in the orientation or angle of these marks. And then the last variable is shape. So the first cell there, we have a rectangle. Second cell, we have a triangle. And then the third cell, we have a circle. And so we can distinguish the difference between those or encode different meaning based on the different types of shape. Now, coming back to this discussion on what is the strongest variable for visual encoding, we would start right at the top. So some of the genius of Bertin that's represented here is not just in the variables, but also in their strength or power. So these variables are also organized from top to bottom, from the most powerful to the least powerful. So if we want to know which variable has the absolute most visual impact, we would start at the top and say that is the XY position on a plane. Basically, our spatial understanding is one of the most powerful representations that we have to use. And if you think about it, from all of our past, from the youngest age, even as a baby or a toddler, we learned that things were near or far, to the left or to the right. And so naturally, that's how our conception of the world was shaped from the very beginning. Then size. So very similarly, we learned at a very young age that some things are larger or smaller, that they're big and small. And this is sort of the same thing that has been represented in visual encoding here. Then we move to value, so we can tell the difference between whether something is shaded or not, has coloration or not, in value. You know, is something lighter or darker. Then we move to texture. So with texture, is something bumpy or smooth? Then we move to color. And color comes into our understanding of how light, different colors of light are processed by our eye, and we will go into that in some detail. Orientation, so are things in one direction or another? And then, of course, shape. Now, shape is the weakest variable, and many of you may not have guessed that in the beginning, but it is, in fact, the weakest variable, which means it does have some performance. I mean, we can get some power out of it, but in comparison to all the other variables, it's the weakest in terms of encoding. So our ability to distinguish the difference between one shape or another is actually fairly muted in comparison to some of the other variables. Now let's go through this representation for the lines for each of the variables. So with lines, with the XY variables, basically this is just the position of the line on a plane. So I'm drawing a line from one location to another on this plane. The first cell, it's from the bottom left to the top right. The middle cell, sort of an S shape. And on the third cell there, from the bottom left to the top right again. So basically, I'm representing XY with a line by saying I'm moving from one point to another, drawing a line. So basically just position. And I also want to highlight to you that notice that the line is basically the same width all the way through. And what I would want you to imagine here with the representation of the line is making a line with a razor blade, sort of the thinnest line that you could make with the sharpest object that you can imagine. Then we move on to size. So in looking at lines with size, with the size variable, notice that in the first cell that is a very thick line. So that helps us encode meaning. in the second cell, or the center, our S shape there, is a medium thickness of line. And then the last one is a very thin line. So the third cell there is a very thin line. So if we're using a line, we can basically show differences using size just by the difference in thickness of the line. So we can encode meaning in that way. Now, when we're looking at the line type with value, so we see in the first cell, basically it's on or shaded. The center cell, it's on or shaded. And then the third cell there, the value is off or null, basically not shaded. When we take a look at texture from the standpoint of a line, so in our first cell there, you'll see that's the most bumpy. So the representation there is the most bumpy line. In the center, that's a medium ridges that I might feel in the center. And then in the third cell there, it might be a smooth line. When I move on to color for the line type of encoding, first cell is blue, second cell is red, and then the third cell is green. Now looking at the orientation variable, I can see when I use a line that my orientation in the first cell is there with that roughly 110 degree angle. So I'm using lines, their orientation, much like I had in the third cell in a point. I'm using crossed lines to represent a line. So I'm using that orientation of 110 or 120 degrees and reproducing that many times to basically demonstrate the orientation of a line. Then when I get to the second or center cell there, you'll see that I have two parallel lines that parallel that S-curve. So I'm using, once again, I'm using the orientation of the lines together. Basically, how close or how far apart are those two lines in relationship to each other as they're drawn in an S-curve. And then the third cell there, I might have lines that have an orientation of, maybe 95 or 100 degrees that are different from the first cell there. So they have a different orientation, a different angle, and that gives me a different line. Now let's take a look at the last variable, shape, for the type line. So I'll see in the first cell there, the shapes that I might be utilizing might be squares there. So I have a whole set of squares, and that's the type of encoding I'm doing, and those squares create a line. Now when I move to the center cell, or the second cell there, you can see there's a whole bunch of different shapes. I might have some different stars or crosses, squares or triangles, so a bunch of different shapes, and I'm using those different shapes to represent a line. And then when I move to the third cell, I'm simply using small circles to represent a line. So you'll see these different shapes are what is being utilized to create a line. I'm not actually, drawing solid with a pencil. I'm actually using several different shapes side by side to represent a particular line. And then we'll walk through these dimensions for the area as well. So for the X, Y, and area, basically we see these numbered areas, basically locations on a plane that would correspond to an X and Y location, different from a different X and Y located area. When we look at size for area, we can see that we can increase or decrease these circles to define a particular area. And you might think about these as, the large circles or mountains, and the small circles represent planes on a geographic map. The area for the value variable, you'll see different shades of lighter or darker to represent different areas or places on this particular plane. Then when we move on to texture, so with the area encoding, we'll see some areas represented that would be very rough if we ran our finger across it, and then other areas that would be much smoother. With color, with the area type, you can see that we would have different areas that would be blue, red, or green. And then with orientation, we could represent different areas based on the angle of the lines. So if we have a number of lines, say in the center, just to the left, and a little bit towards the bottom there, you see basically vertical lines, and they all are vertical, equidistant to each other, and so they all map out a particular area. And then if I want to represent another area on that plane, well, I change the angle of the lines. Say in the first cell there, just to the right of that, I have some diagonal lines that might be at a 110 or 120 degree that run from the center to the bottom right. So that might be representing another area. And it's only the orientation or the angle of the lines that's helping us understand the different areas. And then we come to shape. So in these two cells, we can represent different areas with our squares or rectangles, our triangles, and our circles. And if we put several of them together, they basically map out a particular area on that plane that is different that we can see. Now, I'd also encourage you, particularly on the area, to just scan back from the top toward the bottom. And I think that may give you a little bit better sense of how the XY is the strongest, and then basically the power of the encoding degrades or has less power as we move from one variable to the next till we finally get to shape. And you can kind of tell there it's fairly difficult, or at least much more difficult, to see the differences in shape or area represented by shapes in those visual planes versus those at the top of this list, the X, Y, and the Z. So now we're going to walk through each of these encoding visual encoding principles or variables. So as I mentioned before, these are the essential elements. So learning these and understanding each of these is the fundamental for developing great skill in data visualization. So let's start with the first variable. We have our X and Y encoding, and rather I should say our first two variables, X and Y, encoding as a point. So what we see represented here is we have different plotted points of X and Y, and we see that represented through these different positions. So let's walk through what is represented in the data table here. So we have two different cities, A and B. And then we have essentially three different measures. The first measure is population. So we see there's two different populations, one for A and one for B. The population of A is 3. The population of B is 12. And the importance here is just the relative nature to each other. It could be 3 people and 12 people. It could be 3,000, 12,000. You get the idea. Then if we look at S, S is the surface area in square kilometers. Okay. So in city A, city A basically has a surface area of 1,000 square kilometers. And then if we look at this city B, we have 6,000 square kilometers. Then we have a third measure. And our third measure is basically a measure of density, population divided by surface area. So basically, how many people in a square kilometer? Okay. So our third measure is population divided by surface area. So what we see with our P divided by S measure, we have 3,000 people in 1 square kilometer. Basically the P of 3 divided by the S of 1, which basically will give us a density measure of 3, which essentially says there's 3,000 people in 1 square kilometer. Then we move on to B. So with B, we have a population of 12,000 people in 6 square kilometers, which basically gives us a density of 2,000 people in each square kilometer. So we now have a third measure. And what we'll see here is a representation. On the left-hand side here, we'll basically see our equivalent plotted points for A and B. And if we're just using A and B, and we're not using Z, we're not using any size, you'll see those are all equal plotted points because we haven't added the third variable of size for visual encoding. So that's just the X and Y on the left there. Now let's move to the right. So if we look at the image on the right and see the cross-section of our cities A and B with population, surface area, and then density, we'll notice we're now using the Z variable with size. So let's look at the A for population and compare that to the B for population. So we can see there that our circle of A is basically much smaller, basically representing that 3 equivalent to the 12 size of the circle for B. Okay, so we can see that there's a distinct difference. A is smaller than B there because we've encoded size. Now let's take a look at the surface area. So surface area for A was a 1, and surface area for B was a 6, and we can definitely tell, yep, A is much smaller than B. We have that area of 1 in comparison to that area of 6 for the B. So we can see that very strong contrast between the two sizes there. And then when we look at the density variable, we can see that, that representation of the 3 to 2. So remember, we had a density of 3 for A and a density of 2 for B, and we see that represented with a larger size circle for A and a little bit smaller size circle for B. So hopefully this gives you an understanding of how those plotted points work with the first 2 variable encodings, X and Y, so that would be on the left. And then when we add a third variable of encoding, we have both the X and Y as well as size being used for the Z, so our third variable there. Now let's take a look at an equivalent example. So same cities, A and B, same measures of population, surface area, and density. But notice that here we're encoding basically size for the z-axis in a different way. Okay, so let's take a look at this here. So instead of a plotted point, we see lines here. Okay, so we might have a comparison of lines of A and B here. And then when we move to the right here, in measures of density, this is where we can really see these different measures stand out. So if we look at the city of A, we will see that we have basically a population of 3. So each one of those squares is 1,000 people. So we have 3,000 people stacked up in 1 square kilometer. And so we can pretty well see how that's much denser, how we have more people stacked up in a smaller space. And then we can compare that to B, where we have basically 12,000 people in a space of 6 square kilometers. And basically our density there is our P divided by S, which is 2. So you'll see there we have basically 2,000 people stacked up in each square kilometer, and that's repeated 6 times. So hopefully that gives you also gives you a good representation of the utilization of the XY as well as the Z axis for size. Now let's take a look at area. So here we have the same XY encoding, and we're also using the Z axis to encode size here. So if we look at on the left hand side here, we have different areas of A and B, and we can see in relationship to each other those particular areas of A and B. So our surface area of A is 1, and so that area represented with the A versus the area represented with city B, which would be a 6. So we can fairly clearly see that, yeah, A is about 1/6 the size of B there. Now when we move to the right-hand side here, we do a couple different things here. First, we continue using size for the third variable for the z-axis, and we're going to give a representation of density here. So you can see surface area is represented in the same way we did on the left. So we have this smaller 1/6 sized area represented by A, and then 6 times the size of A area represented for B. So everything's the same there as it was on the left. But we have changed one thing here. So we put some plotted points in here. And notice that the plotted points in A, that point is much larger, represented by the key there, that is the density of 3, which is a larger circle, compared to the smaller circles, again 6 of them, proportional, that are smaller circles that relate to the key that says those are size 2. So using plotted points, basically the size representation, we can see a density in area A of 3 versus a density in area B of 2, and we can also see proportional representation to each other in terms of the population. Now, moving to the representation at the bottom there, so of that density, now we're changing that z representation to a value versus size. So we're now introducing our next variable, the fourth variable, value instead of size. And this is presented by Bertin a little bit in contrast to the one with the circles right above it. And it goes kind of like this. You can see that the area representation is equivalent to the one above it or the one to the left. So we still see our proportional 1/6 area of A and 6 times A area of B. So we still have that there. But we've made one change here. Instead of using the size, for example, of a plotted point, we've gone to a different variable. We're using a different variable value. And what value basically means is it's shaded or not, darker or lighter, basically the value of shading. So what we see is the representation of density of 3, basically 3,000 people per square kilometer, is represented in A. And then we see the open, blank, or white or null representation of 2,000 people per square kilometer represented in the area for B. And you'll notice that those are exactly proportional in encoding the same numeric information, the same measure information that the diagram above it does, just using a different variable. And so now let's talk some more. We'll give another example of that value z variable. So here we're looking at a map of France, and we can see the XY encoding. Imagine that the very center of squares, both in the view on the left and the right, the very center of that is the XY plotted point. So that's the center of the square. And basically, whether we're looking at the frame on the left or the frame on the right, the center of the square is going to be in the exact same place. So that's our XY variables being encoded. Now, what we want to do is take a look on the left here. So on the left, this is basically value, the fourth variable at work. So we're qualitatively comparing the degree of shading of black to white in the frame on the left. And it goes kind of like this. What if we had asked a question, we had basically said the population density is highest where the value is darkest. And so if I asked that question to you, many of you would raise your hands and you would say, okay, that area with the square in the top left, and then that square on the far right of the frame, that's going to be the highest degree of population. And you would be correct. And if I then followed up with the question of, well, what about the least dense population? And you guys now, having fully caught on to the way this variable works, you'd say, yes, down in the bottom left-hand corner of this frame, that's the least dense population, and then it's maybe just slightly more dense in the bottom right, and the square in the bottom right, and maybe the square all the way at the top of France there. So what's being encoded here, and you'll notice that all of these squares are the exact same size. So there's no difference in size. So we're not using the size variable at all. The size variable is not encoded in the left-hand frame. We're simply using the x and y coordinate, basically the position, and then the qualitative value of lighter or darker to encode our measure of population, for example. Now let's look at the right-hand frame in contrast. So if we were to find the very center point of each of these squares, we would notice that it's the exact same location that it was from the frame on the left. Now what's different about the frame on the right is we have not changed the qualitative value, so you see they're all shaded exactly the same. So we didn't use the value variable at all, but we did come back and apply the size variable. And you'll notice that each of these squares is a different shape size. And so here we're using the size variable. Again, we could discuss it as population, and we would come to the same answer to those questions. Where's the highest population in France? So we'd see there, kind of in the top left of of France, that's a high population, as well as the far right. We see a big square there, so there must be a lot of people there. And then if we ask the question, again, the same follow-on question, where's the least populated places? We'd see there the very tiny square down in the bottom left-hand corner of visual frame 2. And then just a little bit more population in the bottom right-hand square of frame 2. So hopefully this gives you a very nice contrast between the two different types of variables, value and size, that we're encoding here. So next we'll discuss texture, the visualization principle of texture. So we'll start with the point. So if we look at points on the top left-hand part of your screen and look at the image there, you can see that we're utilizing texture to go from perhaps the negative end of a spectrum, neutral in the center, to a positive part of the spectrum. In the spectrum that's on top, the visual squares that you see on the top, you'll see a number of large points. So if you can imagine, that's sort of the most negative part of the spectrum. Then we move one square to the right. Our points are a little bit smaller, a little bit more focused. So we might have a very rough texture on the far left-hand side. It gets a little bit smoother. Then in the center, sort of a neutral. Then when we move to the right, we have a positive, and you can see the gray of that box might have a textured pattern within it, and then a more significant texture in the box all the way to the right. Looking at the sequence on the bottom, so we might start with basically no texture on the furthest left, then some points with a little bit of texture, and then points with quite a bit more texture. Then the overall surface has more texture than that, a little bit more refined texture, and then finally the most texture over on the right-hand side. So that's how we might look at texture with points. With a line, it might be represented this simply. So I might take the first line in the top left, that's kind of begins at a 45-degree angle with the large dashes. And if I ran my finger across that, it might be very rough or very bumpy. Then if I went to the line all the way at the bottom, starting on the left, there might be some medium ridges there. And then if I looked at the line in the center, that one might be the smoothest of the three if I ran my finger across there. So that's how texture might be applied utilizing the line. And then finally, in the bottom right-hand corner, if we look at area, we can see different areas, perhaps of a map, and you'll see we might have the white that's very smooth, sort of an absence of texture. Then we might have some smaller dots or some smaller points, a little bit more texture, larger dots, quite a bit more texture. Then we move to the light gray, dark gray, and then finally the black to have the most texture. So that's how texture might be laid out with a point, a line, and an area. Now let's move on to the principle of color. Now, perhaps everyone, when they began taking this course, had the perspective, oh, color, man, color encoding, color's the thing, color, color, color. And we're all attracted to color. There can be no doubt about that. But we should also keep in mind where color falls on the overall hierarchy of sort of encoding power. Keep in mind that it's quite a few variables down. It's maybe somewhat in the center. It's sort of a middle range, if not a low in terms of power definition, visual encoding. But let's talk about how it works. So the way color works is we have red, green, and blue cones in our eyes that receive color stimulus. So they're sort of like receptors that are looking for those three different combinations of color. Now, color is provided by filtering the or reducing the amount of red, green, and blue. So it's a little bit different than what we might initially think about how color is put together. You know, I think many of us, we may have fond memories of some of our first art assignments, and we were blending different colors and putting them together. So we have sort of a natural tendency to think that we're mixing components together to provide color. And there's some truth to that, but the reality of how we create a color is through filtering out of particular types of light or color stimulus. So it's the filter or reducing that's creating different color, not necessarily the adding. It's the subtracting of color. And then the fourth aspect there, often the A in RGB, so the RGB stands for red, green, blue. The A measures the amount of opacity, or how transparent or not transparent is the color. And basically there's an arrangement of light to dark that can provide an order. So we'll come back to that point, but let's just walk through sort of how we receive color, or what color actually is. So we'll start with our blue dots in the bottom left-hand image. And what you'll see in that top row that begins in the first box there, you'll see a blue circle. Now, what we're representing here is the blue, the red, and the green, basically cones, if you will. So we're representing what those circles are in each of these. So if we're looking at this first position here, what we see is that we have blue completely unfiltered. So there's no filter there at all. But the green is completely filtered, as is the red. It's completely filtered. So we don't see any green or red there. We only see blue. And so the result of what we see is blue, which seems pretty straightforward. Let's move on to the next one and how some of the filtering creates unique colors might be helpful. So in the second box here, we have blue, completely unfiltered. We have green, unfiltered, but we've completely filtered out red. So there's no red whatsoever. And you see it creates sort of a blue-green or teal color. Now we'll move on to the third box. We've completely filtered out blue, and we've completely filtered out red. And then we haven't filtered green at all. So the result that we see is green. Moving on to the fourth box, we've completely filtered out the blue, but we have green unfiltered and red unfiltered. So as a result, we receive yellow, or we see yellow. Moving on to the next box, to the fifth box, we've completely filtered out blue, and we've completely filtered out green. And we haven't filtered red at all. So the resulting color that we see, of course, is red. And then the sixth box here, we have not filtered the blue, we've completely filtered the green, and we've not filtered the red. And so what we see is basically a purple or magenta. That is that red and blue coming through. Okay, so hopefully that gives you a feel for how screening back or filtering red, green, and blue light gives us resulting color, and how basically all colors are a result of filtered red, green, and blue. And then I mentioned to you that we would come back to arranging colors for meaning. And so what we see on the bottom right hand image there with the 10 and the 11 is an arrangement of color from light to dark. And so if we look at the 10 there and view that color range as a scale, so we start off with yellow, the lightest, then we go to green, then we go to orange, then we go to red, blue, purple, and black. So we've gone from the lightest to the darkest. And what that does is basically it provides an order. It gives us a little bit more information encoding in that not only does each particular category receive a color for encoding, but the relativeness of the lightness and darkness also gives us a better understanding of value of the gradations between. And we have to do that arrangement of light to dark if we want to know the gradations in between. Otherwise, these will just be mutually exclusive color assignments that don't really have a rhyme or reason. Now we'll look at alignment. So alignment is typically a little easier to interpret than shape. Let me sort of explain what alignment is. So if you can imagine that we have dashes, and those dashes, we can put dashes straight across. Basically, we could say from left to right or east to west, west to east. We could also put dashes from top to bottom. That might be from north to south. We could also put dashes, say at a 45-degree angle, from the bottom left moving to the top right. And so each of those sort of degrees that we might find in the compass or on the face of a watch, if you will, each of those differences in degrees and how we make the dash is known as alignment. So how have we aligned basically the lines? And what we'll see here in this image that's in front of you is we've used predominantly little dashes, basically points that are more like a dash. We do have, in the case of the Samo tribe here, we have actual points that we're using, or dots. And we even have some X's. So we have 2 lines that are aligned perpendicular there. And so what we can do with this encoding of alignment, we can see in this image the geographic location of different tribes. So, for example, the Bolo Oele, that's all our sort of left or right dashes. And we can see where those tribes, members of those tribes might have lived. Moving on to the Bolo Fing, so we'll see some representation for those tribes in the bottom left-hand corner of this image near that large number 4. And then just reading down, we can see the Pule. That's a north to south dash, and we can see where they might have been represented on the map. Perhaps at the top left, as well as scattered through some of the center and right-hand side of the image. And basically, proceeding through, you can see representations of several different tribes. And this is an example of how we can use the alignment of different dots or dashes basically to represent location or visual location or encoding in relative proximity to each other. And alignment, as we've described here, can also be used in combination with size. So we see that here. We have some of our dashes are different sizes to help encode a little bit more meaning. And then finally, our last principle is shape. So shapes must be a certain size to have visual meaning. So if you'll take a look at the image in the center of the screen. So first I want you to look at the very last row of shape images. So we're looking at that. We can see that it's a line, and for some of the shapes, particularly when they're sort of like a line or that Eiffel Tower type shape, or the TriStar, we can see that it's a little bit different, but particularly when we get to some of the different shapes of stars and circles, hexagons, pentagons, squares, it's very difficult to make out the difference between them when they're very, very small. Now, if we read up to about the third or fourth, or definitely the fifth row, the very top row, well, we can make out and distinguish the difference in shapes there. And so this is a representation of what we mean when we say shapes must be a certain size to have visual meaning. That's what we're showing there. And then when size contrast is low, shapes have very small utility. And so if you look at the image at the bottom, you'll see a bunch of shapes. Those are squares and circles, sort of some rectangles, and you'll see different shapes. But it's very difficult to make out what's going on here because of the sameness of the shape size. So many of you guys will be able to see that there's a word printed out here. It's UNESCO, but we have to stare at it for quite a while because our shape size has very low contrast between them. They're all pretty much the same size. So, and again, shape is going to be the weakest of each of these encoding variables that we've discussed. Now, over time, folks have put together different guides for data encoding. So basically, utilizing some of the great work that Bertin has done, folks have given sort of a guide on, well, when might I use different types of data encoding? And so here we see some work by Noah Alinsky and Julie Steele. And I'll walk you through one or two of these just so you can see how it works. So there's an example on the left. The first one we see there are sort of 3 points or circles. The encoding is their position or placement. And think about those circles or points plotted on an XY axis. Can they be ordered? Yes. Useful values, infinite number. We can have as many plotted points as we wish. Does it represent quantitative information? Yeah, fairly good. Ordinal, good. Categorical, good. And relational, good. So you can see it's sort of like it says, it's a guide to help. We might look at the third one down, a couple of bar charts there. Couple of bars. The encoding is the length of the bars. Can they be ordered? Yes. Number of useful values, quite a few, many. Good for quantitative, yes. Ordinal, yes. But maybe not quite as good for categorical or relational. So we see those basically not engaged there. Okay, so this gives you a sense of sort of how to read through and view these. We'll do color and then we'll move on. So if we read all the way down to our 3 colored squares there, we've got a blue one, a red one, and a green one. Encoding, of course, is color. Is it ordered? No. Useful values? Well, few, maybe less than 20. Very good for representing categorical information, but not much else. So hopefully that gives you guys a feel for how a guide like this might work. Now let's talk about the principles of Edward Tufte. So Edward Tufte rose to prominence in the 1980s, basically extended the work of Jacques Bertin a great deal, applied sort of the methods of the statistician with a great deal of focus and study in design. And so some of the principles that Tufte has provided for us, maybe the first one, show the data. That might be the most important one. And what Tufte means by this is represent the data and make sure that you're showing it in your visualization. Don't hide it. Don't over-summarize. Make sure that you're showing the data. We want to induce the viewer to think about the substance of whatever data we're representing or presenting. We want them to think about what's real and what's going on here. What is this visualization trying to tell me? Avoid distorting what the data has to say. We want to make every effort to make sure that our visual encoding and our representations are true to what the data is. It's a smart idea to present many numbers in a small space. So often Tufte is a great advocate of data tables. We want to try to make large data sets as coherent as possible. So we want to use the capabilities of visualization to represent sort of a coherent view of that data. We want to create visualizations that encourage the eye to compare different pieces of data. So if we can get our audience, basically encourage them through visual representation to compare different pieces of data, that's very helpful. They'll get a deeper, richer sense of the information and what it's trying to communicate. Revealing data at several levels of detail is often a good idea. We might have an overview, sort of a mid-range, very detailed or granular data to give the audience a sense of what's going on in the data set. We want to serve the purpose of description, basically describing what the data is or what the phenomenon in the data is. Exploration, so we want to utilize the visual representation to explore data sets. Tabulation, so we may need to add up, sum, mean, etc. Or decoration. And finally, we want to integrate with statistical and verbal definitions of a data set. So we might also want to bring in some statistical information as well as text or verbal definitions to help bring the audience to a better understanding of what they're looking at. Now let's dig into this show the data piece at a little bit deeper level. So first, let's take a look at these different data sets. So these are 4 different data sets, and I'll explain, sort of highlight these for everyone. So first, we'll have these values here, these measures is the X for the first series, 1, and then the Y for the first series is here, okay? Then if we look at the second series, so here's the Y, and then the X would be the same set of values here for 2. Then for 3, same set of X values. There's the Y of 3. And then for 4, we have X and Y right here. So basically 4 series of numbers. The Y's 1, 2, 3, 4. And then the X's 1 through 3 is here and 4 is here. Okay, so basically think about these as different coordinates. I might come through and say, hey, I'm going to plot plot all these on XY. Maybe I'll add these up and take the means. Okay, so we can add these up and take the mean of X and the mean of Y. Okay, and so if we take each of these and add them all up, sum them, and then divide by the frequency 11 for each one of them. So if you'll take a couple minutes and add up each of these, and then consider if all of these, what we have here. So as you guys begin to work through it, you'll figure out that for this series here, basically we have a mean of 9. We also have a mean of 9. And this, so for all 1, 2, 3, and 4 x's, we have a mean of 9. And then for the y's, each of these, 7.5, 7.5, 7.5, and 7.5. So looking at combination of the two for series 1, we have a mean of 9 on the x, 7.5, 2, it's 9, 7.5, 3, and 4 are exactly the same. Okay? Now, here's the question. Are they the same? So as we advance, we now have XY plot of each one of those specific measures. So if you'll recall, our mean of X and Y on all 4 of these series is exactly the same. But are they the same? And this is where show the data comes into play. If we only represented the mean, we would never see the differences between these. But when we represent these visually at a lower level of detail, basically representing each one of the measures. So here, maybe the first one we have 10 and 8.4. So we might see that represented, and each one of the measures is represented here. Now, when we represent at that lower level of detail, we can tell that these series are not the same at all. We have these back and forth across a linear line. This one comes underneath, and then it has an outlier here. This one has sort of a curve, and this one is a straight up and down line. Now, pretty remarkable that these measurements could all produce the same means for the X and Y for each of these, but they in fact do. And so this is just a reminder on sometimes we need to show the data or represent the granular detail to truly understand what's going on in a data set. Now, another historical example of data visualization comes from Florence Nightingale. And these are famously known as the coxcomb diagrams. Basically, they work sort of like pie charts that work in a radial or a radius. So we'll see different measures. You'll see that time works on the radius. So we have April, May, June, July, August, September, October, November, December, January, February, March. So you can see basically a slice of pie or a radius for each one of these months. And what's being represented here is a visualization or a diagram of the causes of death particular war. And I think, if I remember correctly, what's represented here is the Crimean War, I believe. And what Nightingale was trying to do is basically illustrate that many of the causes of death were preventable and were not necessarily from violent action in the war, so much as preventable diseases that came from participation in that activity. And so what we see here, we see different areas of blue, red, and black measured. The blue wedges are the area for the deaths from preventable diseases. Red wedges are basically deaths from wounds, and then black wedges are deaths from all other causes. If we only were to look at deaths from the wounds, we would see a much, much smaller picture of what might have occurred in that war. If we incorporate, so sort of these black wedges or all other causes, and then you start seeing the preventable diseases really taking on the majority of the cause of death in these months. So a couple of things to consider here. One, I want you to critique the visualization here. What sort of biases are built in? What works well? Maybe what does not work as well? So first, as we mentioned before, it's a very unique treatment of time. So typically we think of time as moving along the x-axis, sort of an arrow of time. And so there's a sort of radial or circular representation of time here, separated by each month. So very interesting, but also has a particular bias embedded in that sort of the radial section for each of the months is equivalently allocated. So sort of a little bit of a bias built in when we do pie slices. It's just a reality, a feature, if you will, of this style of visualization of coxcomb diagrams. The other thing is that these colors often overlap, and that can make it somewhat difficult to read and compare. It has some of the same effect as a stacked bar chart that you might see. So might have some inferior aspects to the encoding, but as well was created a long time ago, basically April and March 1855. So good example. You'll see this many times in visualization. So here is a modern example of the coxcomb diagram. So this is brought to us by Bloomberg Business Week. Basically a diagram of revenue earned from one of the recent Star Wars movies, The Force Awakens. And so what you'll see here is if we look over each of these different categories of revenue, there's a video game category, different video games. Or this was Infinity 3.0, this was Battlefront, the international box office, TV licensing, U.S. and Canada and international, DVDs. It covers basically less than 2/3 of what the original Star Wars made, adjusted for inflation. And while a fairly sizable piece of pie here, that being the box office sales for the U.S. and Canada for this film, if we look at the biggest player in this game here by far is the merchandise that's sold that goes with this particular movie. And so we're able to pretty readily make comparisons between the different categories and which might be the best revenue generator. And then as well, we have sort of a large figure here that captures our attention, $9.6 billion, which is what Walt Disney made for this particular film. On a little insight here, that revenue number is more than twice what Walt Disney paid for the entire franchise of Star Wars from Lucasfilm in 2012. So basically, from this one movie, they've made their initial investment back 2 times over just from this one film. So now we'll discuss the area line diagram. This is a line diagram, basically a trend line, many of you are used to. And then we also have an area line diagram here. So this is basically capturing the area. And it's overlaying these 2 important measures together. So here we have U.S. crude oil production in barrels per day. And so we see that's climbing all the way through 2016. Our timeline, basically our x-axis is our arrow of time, 2011 2016. And then our y-axis is million barrels of oil per day. And then what we have here is the price line, basically the price per barrel over this same time period. And most importantly, for this data visualization, what we'll see is the price point dropping considerably here. And even as the price point drops, what we would expect is for production to follow it down. Yet what actually happened is production continued to climb or stayed in a plateau formation while the price dropped significantly. So basically, the title of our visualization here is Defying a Downturn, which in essence, all of our producers were defying this downturn in price. But as we all know, that cannot be done indefinitely. Here is a column line diagram. So a little bit different type of data visualization, where we will see basically columns, sort of like a column or bar chart. Each one of these, the way this is laid out here, is the GDP, whether it's positive or negative. And then what we've overlaid here is that price per barrel of oil in the line or trend diagram. So we've overlaid that on top of the budget balance, positive or negative. Basically, if we have negative, the budget was not balanced, there was a shortfall, and if it's positive, there is a budget surplus. And our visualization here basically asserts that there are better times than others to be the bookkeeper for the country of Russia. And so we see the Russian budget, so it's negative here. The last finance minister joins here, and we can see very positive budget cycles. Of course, we also see a positive uptrend in the price of oil. Then the price of oil has a very negative effect here, very negative downward trend. And we see that significant impact on the Russian budget, basically going negative here, having shortfalls. And then we also have an insider note here that the finance minister's tenure ended here. And we proceed on a little bit further, a little bit of an uptick here, but then back down. And the summary of this data visualization is given the downward trend in the price of oil. It's a very good time to become the bookkeeper because the price of oil is no doubt will advance at some point in the future, and along with it the budgets, and the new bookkeeper will look brilliant. So here's another visualization. What can we see? So cheaper oil was supposed to spur consumer spending, but so typically when the price of fuel drops, that makes the price of all other goods cheaper, and so consumers tend to spend more. And so we have a side-by-side data visualization here. We have the price of gasoline, so downward trend of the price of gasoline as well as the downward trend of the price of oil. The change in prices of gasoline hasn't really matched crude's drop, so it's recognizing that there's a difference in the trend line on the price of gasoline versus the trend line on the price of oil. And then we also see the forecast for household spending growth has dipped since the beginning of the year. So our expectation with these downward trends is that we would see this upward movement in the expectation of spending. Basically, all of this amount, uncaptured revenue, because gasoline and oil is at a cheaper price, is still sitting in the consumer's pocket. So we would expect them to be spending it. And to some extent that happened. But then we started seeing those forecasts fall off again. And so this is a little bit going against the conventional wisdom of what happens to consumer spending when the price of oil drops. Now, we've looked at a handful of different types of data visualization. Let's have a quick conversation about what is an insight. So if you will, take a close look at this particular data set. So quick overview. So we have the number of players, player's name, their birth date, and what position they play. So spend a few minutes analyzing this data set. See if you see anything unusual. Okay, so let's take a look at this. Data element by data element. So first, let's look at numbers. So 1, 2, 3, 4, 5. So nothing too unusual here. Basically, okay, we have 21 different players. By the way, these are different players from the Canadian hockey team, the Medicine Hat Tigers. Here are the players' names. Now, in looking through their names, we might find some sort of interesting backgrounds or common backgrounds. We might find something there, but nothing really stands out here. Lots of different names we look through. Now, when we get here to birth date, let's take a look at this. January 1st, January 3rd, January 5th, January 12th, January 26th, January 27th, February 1st, February 14th, February 20th, February 21st, February 21st, February 24th. So I'm more than halfway through the list, and notice that I'm only 2 months into the year. So half of these players were born in the first 2 months of the year. I might go a little further. March 15th, March 26th, March 29th, April 16th, May 26th. Almost 2/3 of the number of players were all born in the first 4 months of the year. Is that normal? We should ask ourselves, is that normal? So let's discuss what might be normal. So if we took 12 months out of the year, we had roughly 20 or 21 players. We would expect that 1 or 2 players would be born in each month of the year. 1 or 2 in January, 1 or 2 in February, March, April, May, June, July, August, September, October, November, and December should each have 1 or 2 players represented in each of those months. Yet we don't see that at all. that would be a normal statistical distribution. So what we see is 2/3 of the players are distributed in the first part of the year. This is what we might call an insight, something very unusual that's going on with the data. And if we look even a little further, we'll notice that there's not a single player born in the last 3 months of the year. So basically no players, no representation at all for 1/4 of the year. That is truly unusual. As unusual as it is to find more than 2/3 of the player born in the first quarter of the year. Now what's going on here is basically there's a cutoff date for grade school or junior hockey playing, and it begins at a very, very young age, perhaps at 5, where the cutoff is such that the players that were born in January, February, and March are always the largest children. And so they are selected for the team first, even at the very young age of 5, because they have just a little bit more physical size. Then the next year, what happens? They go all year, they get lots of coaching. Then we go to the second year. Well, the second year, this process repeats itself. These players born in the beginning of the year are also just a little bit larger than their peers, but they also have the benefit of getting a lot more playing time in that first year. So there's a snowballing effect into the second year, and that happens again and again and again and again, year after year, where the players that are getting the most playing time and the most coaching are those that were born in the first part of the year, way back when they were selected at 5 years old. So this is a good example of an insight in a small data set. In summary, questions exist at multiple levels of information. So we may want to show a higher level, a summary, the mid-range, as well as granular detail, or different combinations of each to get a full sense of the data. Primary variables of an image are the X and Y dimensions with size and value in the Z dimension. So these are our X and Y dimensions as well as our size and value in the Z. Those first 4 are the most powerful encoding variables that we have in terms of data visualization. And we also have texture, color, orientation, and shape, the additional 4 data visualization variables that can help us encode. All 8 are useful in encoding data visualization, but remember that these all work in an order of power, if you will. So the X and Y plotted dimensions are probably the most powerful 2 variables. Then we get to the Z of size and value, a little bit less powerful, but still quite powerful. And then, of course, we go through texture, color, orientation, and last but least, in terms of encoding power, is shape that make up the differential variables. And we've also provided a financial example of data visualization that you might recognize the approach if you want to study on your own and follow up and take a look at this.